I don't have anyone who's introducing me because this is actually the first webinar in a series that's being run by the Materials Decarbonization and Sustainability Center. So I will be introducing the following speakers, but since I'm the person doing the introductions, hello, I'm Sabbie. I'm a professor at UC Davis. I'm also faculty scientist at Lawrence Berkeley National Lab. And this is, again, part of a series that we're running out of a new research center on campus that's really tied heavily into trying to find pathways to mitigate carbon dioxide emissions from materials production, as well as improve other aspects of sustainability. So damages tied to inequities and those sorts of additional environmental burdens. As I mentioned, handful of first slides are actually reflection of what you all entered when you logged up for logged in rather for this particular webinar. So thank you so much for answering those questions. Just so you have a sense of who is in the audience, we actually have a really good representation from government, both state and federal, as well as industry in the audience today. And then, of course, we also do have a fair number of students and academics. It is, after all, a university, and some groups from nonprofit organizations. We also have a handful of folks who did not fall into any of those categories, but you'll see that the vast majority are in one of those four categories. We also had asked what the audience thought were the biggest challenge associated with decarbonizing materials, especially the ones that are currently being encountered by the groups who have decided to join. It looks like the largest issue that was reported was economic barriers for a known strategy. So strategies are available, but they might not necessarily be ones that can be easily implemented based on economic parameters. The next most prevalent response to this question was limited market adoption and drivers for low carbon alternatives. So again, kind of one that's tied to our marketplace is a main issue. In addition to that, we asked what were the most pressing issues tied to decarbonizing materials that needed research focus. The two most commonly selected answers were understanding environmental impacts throughout the supply chain and validating low carbon alternatives. So happy to share more of the results if anyone is interested, but thank you again for answering those, because part of what we want to do at the center is actually come up with solutions that will benefit the parties that have decided to join this webinar. So having a sense of what you need is really, really valuable to us. So thanks for responding to those. Okay, so with that, let me actually dive into the talk that we prepared for today. So this talk is a little bit of a high level, not too deep into any given decarbonization strategy. Future webinars that will run from the center will be more tied to individual technologies, as well as individual measures that could be implemented, or areas in which we could see greater levels of implementation, whether that be actually in manufacturing processes or in use stages or things to that effect. So again, somewhat high level today, but we're going to talk about a handful of challenges and opportunities tied to four main materials that we really like using in the US and around the world, and trying to understand the main drivers for greenhouse gas emissions for those materials, as well as main decarbonization methods that have been presented in the literature. So given the audience, I'm sure we're all well aware that currently our emissions of greenhouse gases is just not sustainable for us maintaining current use of the planet the way that we have gotten accustomed to. So our trends in terms of carbon dioxide emissions heavily, but also other greenhouse gases, has been continuously upwards. This is leading to warming of the planet. And of course, if we don't have strong measures that allow for us to decarbonize as well as actually create carbon uptake mechanisms from the atmosphere, we will continue to have negative consequences tied to our emissions. Now, this ends up being remarkably interesting for our material products, because in reality, what we end up seeing is that the main drivers for greenhouse gas emissions are not our use of a various number of resources, but rather hugely tied to materials production. So these data are from 2016, where we actually see that about 28% of our greenhouse gas emissions in that year were coming from the production of materials, whereas everything else was the remaining 70%. This is in large part tied to the degree of consumption that we have for the materials. It's not to say that any given material is bad for the planet, but rather how much we need of that material is escalating the associated emissions from that class of materials. So this is a chart just showing the production of some of our favorite materials. The scale is in terms of gigatons. And what you'll see is that it's a bit of an estimate since we don't have total aggregate reporting perfect for concrete, but our concrete is on order of magnitude of 30 gigatons a year is needed. Bricks, we need about 2.4 gigatons. Asphalt pavement, so including the aggregates for the pavement systems, about 2.2 gigatons. Steel, we need just under 2 gigatons. Plastics, we need about a half a gigaton. I have aluminum on the chart. It is there, I promise, but it actually is needed in much lower quantities relative to these other materials. So I really tried to show some of our most consumed materials so you start to understand the layer of scale that we're talking about when we're talking about the source of emissions, as well as what types of alternatives could potentially scale to these magnitudes. And just so that you have a metric you can compare to, water consumption for everything that humans do, so this includes domestic uses, industrial uses, agricultural uses, was about 4,000 gigatons in the most recently reported year. So we're looking at really substantial levels of material consumption. It's oftentimes argued that either sand, which is used as an aggregate within concrete, or concrete itself are the second most consumed materials after water. The reason we have these high levels of consumption is tied to our population growth, our growth in affluence, and the fact that we have kind of been using really similar technologies in particularly the built environment over a long time horizon. So this is just showing you relative increases in global population. As I'm sure you're aware, we recently passed 8 billion people on the planet. And if you look going back in 22-year increments from that 8 billion number, you'll see that we have been growing almost linearly over the last handful of decades in terms of world population. At the same time, we have a growth in affluence. Basically, here we're looking at approximate global GDP over that same time horizon as we had the population growth. And in general, over the planet, we are increasing in terms of our affluence. This becomes a bit of a challenge when we try to mitigate environmental impacts. There's this kind of famous equation that was developed many decades ago that basically said our impact is going to be a function of the population, the affluence of that population, and the technologies available to that population. So if our population continues to grow and our affluence continues to grow, we'll have more wealth and more people needing things that will continue to drive up impacts associated with that consumption pattern unless we have technologies that allow us to counter those emissions tied to these consumption patterns. Again, we end up seeing that high levels of consumption are really strongly tied to our built environment. So just so you have a sense of where our material resources have been going, this is all materials consumed from 1900 to 2015. As you can guess, some estimates have been built into these values, but basically what we end up seeing is that approximately all of the food and feed for animals in terms of mass, all of the resources for energy in terms of mass, about equated all of the mass that we put into the built environment. So substantial needs for the built environment, especially when you take into consideration that the built environment lasts a lot longer than how quickly we use our energy and food resources. So a really large pull in terms of both demands as well as emissions. So with that in mind, it's important to start to consider how do these classes of materials influence our emissions as well as our decarbonization strategies. First of all, we're probably not going to get rid of building materials, right? If we have a growing global population, growing affluence, we're going to continue to build up infrastructure and the built environment for those groups. So we still need the structures and services tied to these materials. And also in areas where we have deteriorating infrastructure, we're probably going to need to do replacement, et cetera. In order to make those materials, we have a degree of resource consumption. We also need a fair bit of energy to make those materials. And then, of course, we also consume energy tied to our structures and services. So, for example, the lights are on in my office. I am consuming energy in a built environment as we speak. We also need structures and services to actually get our energy resources out to where we need them. So this is not something that happens in a vacuum. We actually see cycles already starting to build into this particular platform. And then on top of that, we know that we don't have any perfectly efficient systems. When we produce materials, we also produce a little bit of waste. We have our greenhouse gas emissions, both from processes as well as from energy resources. We also are forming other environmental impacts. So for example, air pollutants associated with certain types of reactions could get formed. This in turn means that we have other burdens tied to our consumption of building materials. These include things like water demands, they include things like health impacts. And so when we look at only one aspect of this particular issue, I want to decarbonize building materials, it's easy to actually miss another portion of this really complex network. So it's very important to actually analyze all of these together so that we come up with solutions that both lead to decarbonization as well as mitigate other environmental burdens concurrently. That said, this is a decarbonization talk, so I will focus myself back in on greenhouse gas emissions. This is the same chart we saw before where we had 72% of our emissions are from other and 28% were from the building material or from materials in general rather. And here you'll see the breakdown of about where those emissions are coming from. So a substantial amount is tied to iron and steel. A good amount is tied to cement production, a fair bit tied to plastics, and then of course there are other materials that we produce as well. Just so you have a sense of where those emissions are coming from for the individual classes of materials, and this is a dense figure, so we'll stay on this slide for just a second. I realize I am a fast talker. I do apologize for that. This is just looking at US levels of consumption for materials. So here's a breakdown of the total production of materials that we had in 2019, and you'll see that a fair bit of the materials that we produced were actually coming from primary resources. So we were actually excavating materials or otherwise collecting materials for their primary use to be in these classes of material products. We did do some recycling as well. However, we have more primary production as opposed to recycling. In terms of the amounts of materials that we were producing, you see a pretty substantial amount was going into our cements. We also needed a fair bit of steel. So again, we start to see emissions getting scaled by the magnitude of a resource that's needed. So if we need a lot of cement and steel, we're going to have a scaling effect of, well, we needed a lot of that material, we're going to produce more of it, et cetera. We also had a fair bit of demand for plastics within the US. We didn't have as much demand as brick, although I have that as one of the key materials because there's kind of an interesting aspect tied to brick that we'll get to in just a moment. And then, of course, as we're producing this many different groups of materials, we're going to have carbon dioxide emissions tied to the materials production. A fair bit of it is going to come from energy resources because we're still heavily dependent on energy resources that have greenhouse gases associated with their combustion or other utilization. However, in materials, we also have a fair bit of chemical reaction-derived emissions, basically the emissions associated with the actual formulation of a compound could have a stoichiometric balance that leads to carbon dioxide emissions. Those get lumped into what we're referring to on this chart as process emissions. So the actual process of making this material is going to release carbon dioxide emissions. You'll see that depending on the group of materials, there's going to be higher or lower levels tied to process emissions relative to energy emissions. However, as I mentioned, we've got these 4 classes of materials that we're going to discuss heavily. So we've got our plastics where there's a good amount of energy demand, but we also have things like leakage and other sources of greenhouse gas emissions that we have put into this chart in the process emissions. Cements have both energy-derived emissions tied to their production as well as process-derived emissions. Iron and steel, again, have both energy and process-derived. Brick, a little bit more heavy on the energy-derived emissions tied to its production. So as we walk through where are these sources of emissions coming from, we see that for cement, there are emissions tied to the decarbonation of limestone. This is a simplified diagram showing our 2 key constituents in the production of cement. The fact that we do require a certain amount of energy for the chemical reactions in our conventional cement. And then there are other processing stages necessary as well, oftentimes supplemented through things like electricity. The chemical reaction that is driving a huge amount of the CO2 emissions is tied to the demand for this limestone. Here we're looking at a reaction that facilitates the calcination, kilning, and eventual hydration of that cement, forming our calcium silicate hydrates, but also allowing for a certain degree of release of carbon dioxide. In the production of steel, a substantial amount of our emissions are actually tied to the reduction of the iron oxide when we're looking at a primary steel resource. This is not as big of an issue when we're looking at a recycled steel resource, but a primary steel resource where we're basically taking an iron ore, we have to remove the oxygen, we have to reduce that material in order to get the iron that we want and then form the steel with additional carbon. So what we end up seeing is that with our iron oxide, by and large, we've been using a carbon-based compound to facilitate that reduction. This is typically occurring at a relatively high temperature, so now we've got energy for that high temperature, plus this reduction reaction leading to process-derived emissions. And then, of course, we do have additional stages of processing for this class of materials as well. For plastics, this is just one example of polyethylene, just one class of plastics. But the concept with plastics is we, again, are heavily reliant on fossil resources for the actual carbon in the material. And then on top of that, a fair bit of transportation of the system through things like pipelines, et cetera, and a fair amount of processing. And here we have shown the actual production of the monomers, so that repeating unit that shows up within our long-chained plastic molecules. We also have the catalyst to actually get those monomers to get into the long chain, so the polymerization stage where you actually make those long-chain molecules, as well as other types of processes, including things like pelletization, so that somebody can purchase the pellets and actually shape them into the plastic shape that they want. For these stages, again, we're going to start to see emissions tied to those energy resources, as well as things like leakage of greenhouse gases. For bricks, interestingly enough, and this is a chart that's just reflective of India, there are many different types of technologies that can be used for brick production, but we also end up seeing a huge amount of differences in the actual energy demands for these different technologies and emissions tied to the energy resources. We've remained relatively dependent on fossil resources for our brick production. And as you can imagine, the fossil resources, of course, have associated greenhouse gas emissions from their oxidation, as well as the pollutants that can come from our fossil resources. So in this case, we end up seeing a lot of the drive for the impact tied to the actual energy. Inefficient technologies as well as energy resources are driving up emissions for our brick. So with all of that in mind, we wanted to examine a couple of decarbonization strategies, and I want to introduce it from the perspective of material use. So this is an adaptation of a materials use hierarchy where basically we end up seeing that there are several pathways that we could start to implement reduction strategies, emission reduction strategies. The most effective that oftentimes could get used, that sometimes has barriers tied to things like codes or just general practices, is in theory we could start to just reduce overall consumption. This otherwise is referred to as material efficiency, basically trying to get the same performance out of a material or product while limiting the amount of material that is actually getting specified. So reducing things like over-design or other impacts that could actually drive up overall materials demand. Of course, there are many barriers to the implementation of that. So there's a potential that reuse might actually be a little bit more beneficial for a given application. Some areas of reuse have actually been tied to things like creating standardized elements that could get simply reused. But there's also some aspects of circularity that I will touch on in just a handful of slides. Recycling, tied back to that kind of concept of circularity, is when the material has been used, we are ready to dispose of it, what resources can still be extracted from that material and how can those start to get utilized? Oftentimes there is kind of this sense of potentially having carbon capture and utilization falling into this recycling category. Basically, if we are going to capture carbon dioxide from our flue gas, instead of sequestering, how can we start to utilize that material? And in theory, that's almost like a waste resource, right? We otherwise would have disposed of it to the air. How can we start to reutilize that carbon resource? And then recovery is basically we aren't able to reduce, reuse, or recycle. What else can we possibly do? Oftentimes this would be things that maybe would be categorized as like a downcycling. This isn't necessarily the most valuable way a material could in theory be used, but maybe we have no other way of reutilizing this particular material. And then of course, the last thing that we want to do is actually just get rid of resources. So disposal should be ideally low on the priority list. If we think about how those concepts map back onto our decarbonization for these four classes of materials, for brick, one of the main strategies that is likely going to get implemented first is trying to tackle these energy resources because there are still relatively inefficient kilns in service, and because we've remained relatively reliant on fossil resources. The two dominant mechanisms that could get leveraged are switching out the efficiency of the kilns and switching out the energy resources to the extent possible. There's also been discussions in terms of, can we use other material resources instead of fired clay? But this is if we want to continue using fired clay bricks, how can we start to re-engineer those systems? Again, you probably saw from that chart on the United States, we don't actually produce as much fired clay brick as many other places around the world. But since it is a globally popular material, I did want to have it in the slide deck in general. However, the US is a bigger fan of cement, steel, and plastics, so let's pivot into focusing in on those. In terms of the decarbonization of cement-based products, there are many different opportunities that have been highlighted. I'm just going to touch on a couple here because we're trying to stay relatively high level in this first webinar. But there have been many discussions tied to switching out energy resources, etc., but also switching out the raw materials to the extent possible. Of course, this could potentially change material performance. Within the realm of alternative materials, there have been several different types of alternative cements that have been explored. These have included cements that still require that kilning stage, the production of a precursor to a cement that has gone through a high temperature production stage, otherwise referred to as a clinkered cement. These have included cements that have higher levels of baelite or higher levels of calcium aluminate phases, basically shifting the amount of limestone decarbonation necessary and also shifting the amount of energy resources necessary for that enthalpy of formation. The hope there is that you'll be able to drive down your carbon dioxide emissions while also producing a desired cement product. There are also calcined alternative cements. These are ones that have gone under a decarbonation phase, but not necessarily that same high temperature kilning phases. So these include a couple of different types of magnesium cements that oftentimes fall into this particular category. And then there are also non-clinkered alternative cements that are being explored. These include things like our alkali activated materials, where basically we might be able to scale up production of cements that don't require any calcining or kilning stages if we're able to leverage these products in a given region. Now, we end up seeing that other opportunities for emissions reduction could be tied to simply using a little bit less of our conventional Portland cement and bumping up levels of other types of mineral additives. Just so that you have a sense of some of the mineral additives that are getting readily explored, coal fly ash and granulated blast furnace slag are already well adopted in the industry, but other industrial byproducts are also being more heavily discussed, as are various types of agricultural residues, some of which have been discussed for decades. Others are being more novelly investigated now, forest residues, and also the utilization of cement at its end of life. So the cement product that we've already formed, how can we start to reutilize it at its end of life? We've also started to see that in addition to the use of these resources as a partial cement replacement, these same resources are also getting explored for their potential as aluminosilicate solid precursors in things like alkali activated materials. And we're also starting to see industrial waste be investigated as the alkaline resource within our alkaline activated materials. So basically trying to understand how the use of byproducts from other industries could get leveraged within the cement products. And then, of course, I'm sure you've heard, if you've been hanging out in the cement world, the utilization of calcined clays also potentially as a replacement for, or a partial replacement for, our conventional Portland cements. Just so you have a sense of where our kaolinite is located around the world. I realize it's a somewhat granular map, but hopefully it gives you a bit of a sense as to where these resources are located. The calcined clays that oftentimes are discussed as a partial replacement for cement are typically leveraging high levels of kaolinite in those particular materials, thus allowing for a partial replacement of the cement with a material that has lower emissions tied to it. In terms of our steel production, there's actually several ways to manufacture steel. First, we start off with the synthesis of our actual iron, so trying to get rid of that oxide, assuming that we're starting with a primary material. In an integrated steelmaking process, one of the more common processes is the utilization of blast furnace slags. So in this case, basically what we end up seeing is the use of iron ore as well as a metallurgical coal that facilitates the formation of an iron sans oxide in a blast furnace. Now, we could use steel scrap in the blast furnace as well, but the blast furnace has been really heavily used for the primary production of iron. After this stage of iron making, we then go on to, again, use a furnace, in this case, most commonly a basic oxygen furnace, that facilitates our production of the actual steel products that we heavily desire worldwide. There is also electric steel making. In this case, what we end up seeing more heavily is when we're looking at a primary production of the material is the utilization of direct reduction methods. Then that direct reduction iron can be leveraged in an electric arc furnace. We see electric arc furnaces get utilized also very heavily for recycling steel. So these types of furnaces get really heavily implemented for the reuse phase of a steel product. Now, I will note we still utilize lime in the production of our materials for these stages of steel production to help remove things like impurities. Lime requires limestone decarbonation for the conventional production of lime. So there is also a process-related emissions, not only tied to the reduction of the iron oxide, but also tied to the utilization of lime resources. We see, in addition to this, that we're not necessarily doing the same processes worldwide. So this is a great map that's basically showing the pre-treatment and iron making in gray worldwide, the secondary steel making, that recycling of steel worldwide in blue. We see primary steel making in red, and then we see combined primary and secondary steel making in yellow. The size of the circles refers to approximate emissions tied to them. And as you can see, oftentimes utilization of a blast furnace and basic oxygen furnace to make primary steel is going to start to drive up emissions tied to the products just associated with the energy efficiency of those systems, the fuel resources of those systems, and the necessity for direct reduction or other reduction of that iron oxide, leading to a process-based emissions. The more that you're able to use a secondary source where basically the material's already been reduced because you're now using a steel product that has had its oxygen already removed, and the more that we could leverage energy resources that have lower emissions tied to them, the more you see a reduction in the associated emissions. In terms of plastics, there's actually many different approaches that folks are taking to plastics. I'm going to focus here in on bio-derived plastics, but again, there's many different tools that one can leverage. So we end up seeing that several of the processes leveraged for plastics actually could be directly replaced with electricity resources, to the extent that you can use a renewable electricity resource instead of our current electricity resources. You can actually start to see substantial emissions reduction tied to benefits of just switching out your grid to the extent that it's possible. We also end up seeing that the incineration of plastics and the utilization of plastics at their end of life can start to drive different emissions profiles associated with our plastic materials. And if our plastic materials can have an idealized energy grid tied to their use, as well as use a bio-derived carbon for the material, there's also the potential to drive down emissions even more associated with this product. Now, of course, this does need to be balanced appropriately. Using inefficient processes with high emissions electricity grids and a bio-derived carbon backbone doesn't necessarily mean you've reduced emissions. It does have to be something that's worked out in concert. So what this chart is basically showing is what can we expect in terms of emissions tied to things like incinerating a product at its end of life, landfilling a product, recycling a product. What does that mean in terms of if we were to switch over to a bio-based material, if we were able to leverage our energy resources, how can we start to change the overall carbon dioxide emissions tied to the plastics industry? And in theory, there are pathways that exist that we can start to leverage to reduce emissions from this growing group of materials. Just as a sense of some of those bioresources that are getting discussed, a lot of them are focusing in on secondary and tertiary feedstocks. So a primary feedstock would be something that we as humans could eat. And the goal is not to offset human feed or animal feed by putting that biomass into plastic, but rather how can we leverage the byproducts of those food crops or other biomass resources that wouldn't necessarily be a primary crop and put those into our bioplastics. So some examples include like reclaimed starch, the corn stover and stalks associated with the materials, the straw from our wheat, the biomass that comes from sugarcane cultivation, so bagasse and molasses products, as well as things like landfill methane. So biodegraded materials in the landfill, how can we utilize that methane resource to synthesize plastics? And there are various different pathways to both fully bioderived plastics that would potentially be completely different than our current plastics, as well as bioderived resources that could be used as the carbon within a backbone of a conventionally synthesized plastic. Now, all of these methods for each of these different classes of materials that I just listed need to be assessed within the framework of what a material is necessary for. So if we're trying to replace a material for a given performance, we better not change that performance. So this is a cartoon a friend once sent me of somebody who's basically showing a scientist that they've made a more sustainable product. They said, we've made your environmental report greener. It now uses 50% less paper, but that is no longer performing the same way as our original system. So with that, we also could start to look at strategies that already fit well within how we're designing and utilizing our materials, but also reduce the net emissions tied to them. So this is actually where that concept of material efficiency starts to come back. If we are able to do levels of manufacturing improvements that are readily implementable, so we have the methods of doing it, but maybe we have a cost barrier associated with them, those can start to be tackled within the life cycle. And then we could also continue to do research on methods that may change performance so that we start to understand under what circumstances would we want other types of measures to get implemented. We can do improvements at the actual product stage, so how we're assembling different resources together to make a product. We could also start to do improvements while we're trying to understand how we're designing and using our material systems. And then, of course, we could also do improvements at end of life. I'm going to give an example as we look at these different life cycle stages tied heavily to concrete, because our group does a lot of concrete research. So you can start to see what I mean in terms of strategies that we might be able to implement faster or relatively fast, and the efficacy of those strategies so that we can start to tackle low-ish hanging fruit associated with emissions reductions as we start to build up research efforts in some of these more dramatic and larger efforts to decarbonize. So within concrete, we could start to look at potentially, let's focus in on the energy resources tied to the materials. Let's not focus in as much on the raw materials getting switched out because, again, that could start to alter our performance. For the mixture improvements in concrete, this includes things like what if we're able to use a proper amount of Portland cement replacement with a nice reactive supplementary cementitious material? What if we're able to improve things like aggregate gradation to improve packing, reduce the amount of paste we need, etc.? Basically balancing out our mixtures in order to drive emissions that way. We also have the potential in the built environment to start to leverage slight differences within design while still meeting design code. So what if we're able to change out our reinforcement just a little bit, stay within the bounds of appropriate reinforcement ratio, but kind of reduce the amount of steel needed in order to drive down emissions tied to that product, as well as can we leverage improvements in the strength of the material or other performance characteristics to potentially need less overall product. And then, of course, we also have the chance for things like repurposing of a system, right? We have used this structure. It no longer is serving the function we originally wanted that structure to serve, but we could use it for something else. To that extent, if we don't need as much new material production, that could be a win in terms of we reuse the materials that are there and only slightly supplement them with additional materials as opposed to building something brand new. And then I'll discuss end of life a little bit separately because circularity is a very rapidly growing topic in each of these different material classes. So let's walk through what we would expect in terms of emissions and emissions reduction if we started to look at strategies that, again, technically we have access to, but they might have barriers in terms of things like codes and cost. Well, the top line here is an estimate for projected greenhouse gas emissions that one of my graduate students put together. So we're going to call that our baseline. And we're going to try to walk through how each of these different life cycle stages can reduce emissions. Globally, if we were able to snap our fingers and switch out our energy grids, we could have substantial reductions associated with using alternative fuel resources. It's not going to completely get rid of our emissions. We still have process-related emissions tied to our cement, as well as other emissions throughout the supply chain. Also, odds are we're not going to use like a perfectly net zero thermal energy resource. So there are going to still be some emissions, even if we do have our thermal energy switched out. But we could have substantial reduction in emissions by doing this manufacturing improvement. Globally, if we were willing to optimize our amount of supplementary cementitious materials, or even just use them more effectively, and potentially use our aggregate gradations more effectively, we could get further emissions reductions for our concrete systems. If we were able to then pair that with appropriate selection of things like compressive strength and other material performance, as well as appropriate levels of steel reinforcement, we can get another emission savings associated with that. And then if we could pair that in with improving the use phase of our materials, repurposing those systems for other applications, for example, we can get even greater emissions reductions by tailoring throughout effectively the life cycle of our products. For concrete in particular, if we were, again, able to magically implement this worldwide, we could, in theory, with these strategies, have a 75% reduction in greenhouse gas emissions. Obviously, these are not strategies that can immediately get implemented worldwide, which is why we also need to pair in other types of decarbonization methods. But looking at methods that have near-term potential, we do see substantial reductions that could be achieved. Now, let's talk about the end of life for these resources as well. Steel and all other alloys, in addition to steel, are actually already very prone to being benefited by circularity. The atomic structure of these resources facilitates our continuing to heat and cool them and reshape them while maintaining material performance. So we're able to, in theory, collect our used alloys and then reform them into new compounds. There could be some deleterious compounds remaining on those materials, so oftentimes we're not going to recycle them to the highest performance alloy that's out there. But for things like our built environment, we very heavily rely on recycled alloys. Now, interestingly enough, the availability of the recycled material varies pretty heavily by region. This is a chart of in-use stock for our steel products. So how much steel is each region currently using? And you can see that that's a pretty wide spectrum in terms of the amount of tons per capita that we're currently using of our steel. And then if you take into account the materials that we recycle could be scrap from the formation of the products, but also are the materials at their end of life when we're disposing of them. Well, if we're already using the material in a region, then we're probably already more likely to dispose of that material in the region. But if we haven't been using a heck of a lot of that material in a region, we won't have as much scrap to recycle. So leveraging circularity for alloys as a method to reduce emissions can actually be much more challenging in areas where we haven't been using steel for a lot of the products that are getting leveraged. In terms of plastics, there are many different circularity strategies that are getting investigated. As I'm sure you're familiar with, there's the reuse of like, let's just continue to use this plastic product if it still is performing properly. Let's wash out our water bottles, etc. There's also mechanical recycling or thermomechanical recycling. So how can we basically melt down our thermoplastics, reshape them into a product that is viable? This could actually lead to a degree of deterioration depending on the number of times the mechanical recycling is performed or whether there are other additives in the product, etc. But also, there's a lot of efforts going into various forms of chemical recycling. These include dissolution to form polymer chains again. It includes depolymerization to form new monomers, which then still need the polymerization to form the large backbone chains that are in our polymers. It also can be the full breakdown of the material to a feedstock, which then needs to undergo the formation of the monomer and the polymerization stage. However, these chemical recycling methods, each have the potential to produce a product that doesn't have deteriorated properties associated with it. And of course, there's also a fair bit of work going into how can we leverage flue gas from our industrial production systems, take that carbon and use that as a potential resource within the synthesis of our plastics. Now, cement hasn't been as heavily investigated for circularity, although there's a lot of work that has started off recently in that area. One of the areas where we have started to see circularity in cement be discussed is actually the one I just mentioned, right? The repurposing. How can we just elongate the use of a system that would have otherwise been demolished? A recent study in California suggested that if we were able to repurpose our concrete systems just within this state, we could have a 40% reduction in greenhouse gas emissions associated with new material synthesis. We also very heavily leverage our concrete at its end of life as a road base, something that was very popular in this area, where basically we're able to crush down the material and use it for the solidified layer that we would typically put below our pavement systems. We also have seen some level of investigation in trying to use those materials as aggregates. Of course, the cement paste, the interfacial transition zone between the cement paste and the aggregate, and then of course the aggregate properties, having that three-phase system be put into a brand new concrete mixture has caused a wee bit of challenges. So these are areas that are getting explored, and in the case of the road base, very heavily leveraged. But there's also been interest in how can we start to recover a high-value product out of our cement. So some areas have included, well, what if we're able to crush down our concrete, get it to fully carbonate by having a larger surface area to volume ratio, and use that as a direct air capture mechanism? How can we start to use our crushed concrete as an uptake mechanism at its end of life? This could be something that's very valuable as long as we don't have too high of emissions associated with the crushing processes. So picking the right equipment at that life cycle stage and right fuel resources. We also have seen work that has been leveraging heat treatments at relatively low temperatures compared to the synthesis of cement in order to basically make a rehydratable material out of cement fines. There's also been a fair bit of work in terms of trying to understand how that cement could be a partial replacement as for lime in our furnaces used for steelmaking, most heavily in the electric arc furnaces for steelmaking. The concept here is that if we're able to partially replace that lime that's needed for removing impurities in the electric arc furnace, then we could potentially create a decarbonated lime resource, basically that hydrated cement, invigorate it, basically having interact with the amorphous silicates that are already being removed as impurities, create a new cement product associated with that effective recycling of the material within the electric arc furnace, and potentially have a lower amount of lime that's necessary for the electric arc furnace to produce steel. So basically trying to recycle these two materials together within electric arc furnaces. There's also been some exploration in terms of using the cement fines that have been carbonated. So we have already exposed it to atmospheric CO2. It has interacted with that CO2. It's bound that material in a carbonate mineral. Now leveraging that resource as a supplementary cementitious material, not necessarily as a cement on its own, but actually contributing to partial replacement of a conventional Portland cement. And there have been many other types of thermal, chemical, and mechanical activation that have been looking at the application of those types of processes to other industrial waste products. So not necessarily circularity within the cement products, but basically saying, here's this other industrial product or process rather that's going on. It's creating a waste stream. How can we valorize that waste stream within our cement-based materials to have overall circularity, even if it's not circular within one product? Now, this all kind of highlights that in reality, if we want to tackle these challenges, we really need to engineer throughout the life cycle of the product. There's many different stages of intervention, and if we want to reduce emissions quickly, in all likelihood, we need to combine several different stages of intervention to hit near-term emissions reduction goals. In more long-term emission reduction goals, we're also seeing a lot of discussion tied to the use of the built environment as a carbon dioxide removal system. Basically, the idea here is that our built environment, as you saw from our earlier charts, it's the largest consumption of materials that we have after water, right? So here's this huge mass of materials that we synthesize every single year. On top of that, this class of materials gets used for an incredibly long period of time. So think about how long we use our buildings relative to our cars or our computers or our water bottles. We are using these materials for incredibly long periods of time. So to the extent that it's a large volume of material that's actually used for decades, we have the potential that this class of materials could actually create temporary carbon storage that is meaningful enough on the scale of dynamic warming potentials to act as a storage mechanism that could support our carbon dioxide removal goals. The benefit of this is that if we're able to leverage at least some of these products for carbon dioxide removal, then we could potentially not need as much in terms of what we're sequestering into geologic reservoir or some other mechanism. So we can leverage our built environment as this reservoir for carbon storage. Now, there's several different strategies that have been discussed within this realm. Some of them truly are carbon dioxide removal, truly rapidly removing atmospheric CO2 and storing it within the built environment. Others have been much more of a storage mechanism. So not necessarily directly removing the CO2, but rather acting as a mechanism that can store that CO2 if you have some other system that is removing that CO2 and creating a relatively purified CO2 stream. A couple of areas that have been explored within this general realm. So if we imagine we've got all of these sources of CO2, transportation, industrial processes, livestock, etc., mainly have been tied to things like carbon mineralization and leveraging biogenic resources. So carbon mineralization would be the utilization of this carbon that is otherwise atmospheric CO2 or would otherwise be emitted to the atmosphere and actually holding it in a long-term storage of a mineral phase. So basically creating a calcium carbonate, creating a magnesium carbonate, and then leveraging those types of carbonate minerals within some other product. Photosynthesis is, well, you probably encountered it many times. So basically the natural process that our plants and other components undergo where they're interacting with atmospheric CO2 to form carbon compounds that can be leveraged for other applications. When it comes to what's being done with these two main pathways in the built environment, we're seeing a lot of discussion in terms of carbon mineralization to form synthetic aggregates. We're seeing a lot of discussion of carbon mineralization to form even carbonatable clinkers. So basically a cement that instead of solidifying with water can solidify with carbon dioxide, but also methods like what I just mentioned a couple of slides ago, carbonating cement fines that have already undergone decarbonation, but now we're going to uptake CO2 and then use those again as supplementary cementitious materials. In the realm of photosynthesis, there's been a huge amount of work. These include things like quite simply trying to leverage woody biomass in a better way, make sure that we have very sustainable forestry management products or processes rather, leverage that woody biomass so that it's staying in the built environment for a very long period of time, holding on to that atmospheric carbon. We also have seen a huge amount of work in terms of the utilization of biochars. So basically charred biomass that could also hold on to that carbon for a long period of time, although dissimilar from past work on use of biochars in soil amendment, a lot of the concepts here are how we can reuse those resources as mild levels of additives and other composite materials. As you can imagine, they do need a good balance of the appropriate composition of the biochar, as well as sometimes things like grinding it down to a high level of fineness, but there's been a huge amount of effort in this area. And then there's also been a fair amount of effort in synthesizing things like the bioplastics that I discussed a moment ago, as well as using biofibers in different types of products that potentially themselves have relatively low strength, but are able to be partially supplemented by these bioresources within the product. Overall, I realize that, first of all, I'm sorry, I talk very quickly. I also have given lecture already today, so that means I talk even faster. The more I talk, the faster it goes. But I wanted to kind of have a quick, overarching takeaway. This is a cartoon from First Dog on the Moon, where basically they have a chart on how we have handled our greenhouse gas emissions. And we know that we need to hit net zero. There's been discussion on both, emissions reduction as well as carbon dioxide removal. However, if we just assume that at some point we're going to get carbon dioxide removal to happen in the blink of an eye, that's really kind of a pipe dream. So the little cartoon is basically showing, we have these continued upswing in emissions and we're just banking on a magic event. And I want to push very heavily away from that kind of concept and rather say, okay, we've got So many different strategies. Which ones can get implemented first in which regions, knowing that different regions are going to be able to adopt different strategies based on the resources they have or the codes that they have. Which strategies can get adopted as quickly as possible? How can we start to build off of those initial adoptions to improve the next tier of strategies? How can we make sure we have the research foundation necessary for the carbon dioxide removal that we know we're eventually going to need, and start to really build up the approach that we have to actually hitting our climate goals. So again, since this is the first webinar for the Materials Decarbonization and Sustainability Center, just wanted to give a little bit more context as to the efforts that we're doing. Obviously, everything that I've discussed so far in future webinars will go into significantly more detail on any given component within that stage. But there's also a lot of work that's going into other aspects of sustainable manufacturing, more areas within circularity. We have several researchers that are looking at how food, energy, and materials can be co-synthesized so that we're, again, not removing any access to food, but rather trying to understand better how these different systems can all work together so that we have the access to food, energy, and materials that we need as a society. A huge amount is going into understanding localized resource scarcities, as well as localized pollution that could cause disproportionate community impacts. So making sure that if we do have a switch in decarbonization methods, that it has a co-benefit to the local community, as well as strategies tied to improving our understanding of value chain related impacts, as well as you can guess from the whole talk, a lot on life cycle assessment modeling and carbon dioxide removal. The center is not just one person. I realize it's me right now. I will be introducing others in future webinars. Current faculty affiliates are shown on this screen. So we have a bunch of folks that are looking into materials, a handful of folks that are looking into sustainable manufacturing processes, as well as life cycle assessment experts in the faculty consortium at the moment. We also are linked with Lawrence Berkeley National Lab. Our current primary collaborators at the lab are all within the energy technology area, which is where the building technology as well as the life cycle assessment programs are run out of at the National Lab. And of course, like all professors, what I've just presented to you was the work of my amazing graduate students. And we have even more students in the center overall. But I really want to do a very strong thank you to the students who put together this immense amount of work. And of course, they're the ones who are going to continue on forging new pathways. If you do have any questions, I also wanted you to have access to my email address as well as our program manager's email address, which is on this slide. But with that, I'm happy to take any questions that have come up for folks. And I realize we've got about 5 minutes left, maybe 10 before we've got to move on to our next thing. So,
Sabbie, so there are a few questions in the Q&A box. First is, in terms of the material demand, do you see any changes in the past and also may happen in the future, and how those can affect the environmental impact?
Yes. So our general material demands, as you can imagine, there's like little dips that occur every time there's a recession or something to that effect, because there is this direct tie to affluence, right? We need the resources, the monetary resources to purchase materials. In general, we have seen continued upswings in material demand as a function of population growth, affluence, and other characteristics, right? Just generalized buildup of infrastructure, for example. To an extent, in theory, material efficiency could start to lower our future material demands if we start to use our resources better. But in general, we've seen that the trends have continued to go upwards. And in some material cases, they are skyrocketing. So plastics is the key example, right? We just have wild growth in terms of our plastics demand. So that answered the demand question. I feel like it was a two-parter though. What was the other part?
Yeah, I think this answers the question.
Yeah. Okay. Perfect.
Yeah. Another question is like we talked about like a lot of like concrete brick stuff, and how about wood as a building material?
Yeah, I actually kind of had expected somebody might ask that. So, I had a backup slide. Wood has many benefits associated with it. Rather, I am a big fan of wood products. In addition to the fact that it is a material that is synthesized through photosynthesis flat out, we also have this kind of benefit tied to quite frankly, how humans interact with it. We oftentimes actually see a social benefit tied to people are more comfortable around wood products relative to cement and steel products, but also it helps regulate things like relative humidity indoors, etc. This chart is showing our US consumption of woody-based materials. So substantial amount of mass going to lumber production, substantial amount going to other wood products. The way that the USGS reports the data from the US Forest Service, they also break out plywood separate from our lumber production, but also used in construction applications. However, a huge amount is going into paper and board, which does not get used for very long. So we do have this potential to store some carbon in the built environment by using these long-lived products, but the products that have, very short time horizons, if we're not disposing of them properly, it could just lead to the carbon cycle actually being accelerated. So if you imagine you've got woody biomass that's taken, decades to grow, then you use it for a few years, and then maybe you combust it for the energy resources. I mean, it's better than coal in theory, but now you've oxidized a product that took a really long time to uptake. So there's a dynamic effect associated with how we have the carbon being removed from the atmosphere and how quickly it's getting returned to the atmosphere. In addition to that, these data are actually a little bit old. We've continued to increase our paper product consumption over recent years. The more that we've enjoyed having things shipped to our homes has actually driven up a little bit of paper demand. With that said, there are also issues tied to forest management. So how well we have sustainable practices getting implemented in forests, and forest fires. So we have seen that the oxidation of our woody products through combustion and forest fires has actually started to affect how much the planet's land mass is contributing to a carbon uptake mechanism. So all of those really need to get balanced in with one another as we look at woody biomass as a resource. So as we look at lumber as a resource. Again, this is not saying to not use it. I'm a big fan of the material, but rather it could be more complex than just we'll use wood instead. Hopefully that addressed the part that this person was asking for.
Great. I have a question myself. So what types of building materials could best be used for carbon storage? Like we talked about emissions all the time. How about?
Yeah, so there are various resources that can actually store different amounts of carbon. So depending on the actual composition of the resource that gets used in the material, there could be a varying level of carbon content. And if you have a different level of carbon content, then the magnitude of carbon storage for any given product can range. However, the largest driver of potential storage is mass. So even if it's a relatively low level of carbon storage within the product, if you're able to scale it to an enormous mass of product, that can lead to a substantial reservoir. So it's actually not too dissimilar from the emission sources, right? If you have more of this material being made, you're going to potentially lead to more emissions, even if it's a relatively low emissions material to make. The scale is going to drive impact side to it. The same thing can be said for storage. If you've got a lot of this material and you can make it store even a small amount of carbon, that scaling could lead to a huge amount of storage within that product. So for that context, as you can guess from the mass diagrams that we had, the materials that have larger levels of consumption and carbon content could potentially lead to the larger amounts of storage if we're able to get the desired performance out of those materials.
Thank you, Sabbie.
I realized that it's actually 2. I think my computer just made a ding. I hope I'm not missing any of the questions, but of course, folks, feel free to reach out. I'll put the slide with email contacts on it. And there we go. So happy to address more questions, happy to give any more context. Again, this is a very high level introduction to the work that's going on, and we'll have more webinars in the future to continue to disseminate the research that we've found. And again, thank you so much for all of the feedback in terms of, areas that you find important, because that's exactly what academics want to do, is we want to help come up with solutions. So fantastic. All right, with that, perhaps we will part ways, and thank you so much for logging on for this webinar.